Good morning, everyone. I believe everyone is so serious today. I would highly appreciate if you become a bit relaxed and try to give me the scope to present myself in a more relaxed fashion. Anyway, so I believe although my research is mainly related to the networking part, many of us does not really relate to my part. So maybe they won't understand it properly. That's why I try to keep my presentation as simple as possible for all the viewers, so that even the non-networking guy, they can also understand at least some most of the part. Okay, so for my presentation today, I'm presenting but a bit interesting thing, that is the elephant sharing the highway. So as you can understand from the title, the elephant here I mean the big amount of data that we people, the scientists, are generating in our day-to-day life. So when we are trying to transfer this big amount of data through our network from one place to another, so the network is actually dealing with a significant amount of resources that needs to be exhausted for dealing with that data. So now how we can distribute the data in the network so that the network can actually handle it properly. So that's the main purpose of this research, to see how the network deals with the data. So in our day-to-day life, when we are using the internet, I believe most of us always come with these three questions. Am I actually getting a higher or high-speed network? Or am I the network, the connection I'm getting, is it reliable and is it delivering me the data in a timely fashion? And also at the very end, we also think, well, am I deprived of something? Like, am I not getting a proper share from the network? So all these questions are also arising in the background with the network scientists. So we are always trying to find the answer. And this research, in this in my previous presentation, I'm going to trying to find out with the existing protocol, can we really answer these questions? But the most interesting part is that when we are going to develop some new technology, we also need a lot of data from the existing protocols. Unfortunately, that was not present before our research. So this research, in our research, we mainly focused on developing on that data set that will give the future scientists, the network scientists, to develop future network protocols that will be able to handle the network more efficiently. So that was the ultimate goal of this work. So firstly, we tried to identify the optimal solution from these existing protocols. Then we are also try to examine the interaction between the different protocols that are interplaying in the network, and we developed a data set that will be a future very good background or building block for the next algorithms to be developed for the networking. So here comes the tricky part. I had put a lot of animations here. Unfortunately, that was in PPT, PowerPoint, and the Google slide does not support all of those, so it is broken. Anyway, I will try to simplify the thing. So if we take the network as a whole, so that is the sender, that is the receiver, and in between there are these, we call those are the middle boxes, like routers or switches, whatever. So normally a sender is connected to a router, the sender 2 is connected to a router, and receivers are also similarly connected to a router, and between those routers there are the whole internet. Now we define the connection between a router, a sender, and the receiver by the bottleneck. The bottleneck is the connection between a simplified two routers. When, for example, here in these two routers, the link between two routers that have the data, because all the, if you see sender 1, sender 2 are sending the data with the same link. So the link becomes the bottleneck. So because it is a sharing point of all the senders. So in the same way, if we escalate that scenario to the whole internet, the similar thing happens. So there is a bottleneck. So that is the link we are showing here, that for a simplified version, that between these two routers, this is the bottleneck, which defines that how the network will behave. So what happens in the background if we try to understand the protocols? So there are mainly two key protocols that control the flow of data. One is from the sender to sender, we say that is end-to-end protocols. And also there is one between the middle boxes, one-to-one protocol, that is from here to here, point-to-point protocols. So from the end-to-end, the protocols like TCP, congestion control algorithms, come to play. The TCP has different protocols like TCP, the transport layer that ensures that end-to-end, it is two protocols mainly, TCP and UDP. And in TCP comes for reliable data delivery. And in TCP, there are different congestion control algorithms that actually controls the flow between these senders and the receivers. Now, what happens that in the sender side, when an elephant or a big data comes, the sender divides the data into pieces, and then it puts that data into a queue or in a scheduler, and then it sends the data. So the data actually travels from all the way here by there and comes here. So here, when the data arrives, so it again rearranges the data, because the data can arrive in different unarranged local situations. So they rearrange the data, then they put the data together, and they put the file, whole data to the receiver. So that's how the entire thing works. And now, because the sender, it is not only the sender 1, but also the sender 2 is also sharing the same link. So the senders, both the senders, they try to send the data at the same time. Now there is a problem here, that because these two links have may have some better higher capacity. Now this might have lower capacity. Now how it can deal with such amount of data that is coming as a burst at the same time. So here comes the AQM algorithms also. So first, there are two things in play. So to control this from the end host, there is also a protocol, that is the congestion control protocol, that is working. At the same time, as a point-to-point, the AQM algorithms, that is the active queue management algorithms, that are working. So for example, here there is a buffer. So when from both the side two elephants have come, so the buffer can be arranged in a first in, first out manner. So that is one kind of solution to keep the data and to forward the data. So FIFO or rate works in that manner. And there is also another kind of arrangement like the FQ codel, that is another AQM algorithm that tries to distribute the data flow wise. For example, sender 1 has sent some data, it will put in sender flow 1. Sender 2 has sent another data, it will put in flow 2. So that's how it is trying to arrange the data in multiple flow. So different kind of approaches are there to give a solution. So now it is in this research, our goal was to find out which is giving better performance and build a data set from our experiment. So for the experiment, we use the Fabric. Maybe many of us knows about Fabric. It is a very unique experiment test bed that actually connects from Japan to Europe throughout US. And it provides a huge test bed for us. So we can actually create a virtual network between here, which will utilize the existing network and create a virtual tunnel for us. So we can actually, in a controlled fashion, we can experiment in this network. So although we are actually experimenting with the real network, but in a controlled fashion. So that's the main advantage of the Fabric. So we use that one, and we use such a topology there. So here we have the two senders in the clip zone, and there is the two receiver at the TAC, and we have intermittent the routers at Washington and NCSA. And for the senders, they were connected with 25 Gbps lines, and so far as the receivers, and between the routers we provided a large line with 100 Gbps, but this 100 Gbps was virtually tuned. Okay. So here is the different configurations, and to give a summary, we experiment more than 70K, and the total amount of data, the data set we generated was 16 TB. So this is just a glimpse of the figures that we have generated from here, where different parameters like the megabytes for the congestion window, RTT, retransmissions, all those things are all together here. So in summary, if we see, so the PBR V2 with FQ codel as a whole provide the superior performance overall. In summary, in conclusion, the choice of queuing algorithm, we find that it plays a significant role in determining the network performance. Google VBR v2 protocol shows a better performance in terms of retransmission than HTTP. We use cubic and HTTP in DOE. And if in a conclusion, we can say that combining FQ Cordel queuing method with VBR v2 may offer the best balance. So that's all for my today's presentation, although I overshoot my time. Sorry for that.